To begin with, let's review the typical workflow for ArgoCD. For example, a developer changes the source code, like adding a feature or fixing a bug. Then they commit the changes and push them to the remote Git repository. After that, continuous integration tool like Jenkins detects the change in the app's repository. It downloads the updated code, runs tests, and creates an artifact like Docker image. Finally, it uploads the image to the remote Docker repository. Once completed, Jenkins clones GitOps repository containing your infrastructure code and updates the Docker tag. On the other end of this CI/CD pipeline, ArgoCD continuously monitors the infrastructure repository, and when it detects a change, it applies the update to Kubernetes. As illustrated, CI/CD pipeline is closely interconnected, and in this example, Jenkins is responsible for both creating the artifact and updating the GitOps repository. Now, there is another option, is to decouple CI from CD and make it more flexible. In this case, you can easily replace continuous integration tool for any other, since it will only be responsible for building artifact. In this example, CI tool creates a Docker image and uploads it to artifact registry like Docker Hub. Next, ArgoCD image updater independently identifies a new tag in your registry, and based on a filter, it will either apply or ignore the update. Now, there are two modes available. In the default mode, image updater directly updates the ArgoCD application resource, which in turn prompts the ArgoCD server to deploy a new version to Kubernetes. Alternatively, there is another option known as Git writeback method. The image updater will identify a new image tag and create a new commit in the infrastructure repository. Similar to the standard workflow, ArgoCD server will identify the change and update the app in Kubernetes. Both methods have advantages and disadvantages, which we'll discuss in this tutorial. I'll also provide my personal opinion on which one you should use and why. This tutorial will cover both Kustomize and Helm deployments. At the end of the tutorial, I will demonstrate how to use sealed secrets to encrypt sensitive data, like private keys from GitHub, as well as passwords and tokens for image registries, like Docker Hub. In the previous video, we covered the process of setting up Minikube and deploying ArgoCD. However, I'll provide a quick summary in this video to ensure it's self-contained. If you're interested in more details, please refer to the previous video. Now, let's get started with preparing the local environment for Minikube setup. To spin up Kubernetes, you can choose to use Docker as a driver. Additionally, you have the option to specify the version of Kubernetes you'd like to install. However, if you omit this setting, the latest available version of Kubernetes will be used by Minikube at the time of its release. To verify if Kubernetes is operational, we can retrieve the list of the nodes. If your local workstation has sufficient resources, it is possible to create multiple Kubernetes nodes, rather than being limited to a single Kubernetes node cluster. I personally prefer using Terraform for deploying almost anything. You can choose to use Terraform alongside me, or you can simply copy-paste commands and execute them locally. For instance, if you want to install ArgoCD, you can achieve that by making use of Helm install command. We'll override some variables, such as updating ArgoCD image to the most recent version and disabling HTTPS. Typically, it is preferable to use ingress and terminate TLS on the ingress level rather than on the ArgoCD server itself. We'll use Helm chart to install ArgoCD image updater. Let's proceed with adding this chart repository. Next, update the index to include the new charts. Lastly, search for ArgoCD. The main Helm chart for ArgoCD is Argo-CD, and for the updater, we'll use ArgoCD image updater. It is likely that you may need to customize the default variables by overriding them as per your requirements. To obtain the default values for a specific chart version, the recommended approach is to use Helm show command. You can find the parameters you want to modify in this file and create a new YAML file with the overrides. Now we can create image update.yaml file and define the variables that we want to override in it. One variable we may want to override is the image tag variable to use the latest image. Additionally, we can enable Prometheus metrics by setting metrics enabled variable to true. We can deploy the Helm chart using Helm CLI or create a Terraform file to automate the deployment process. Let's name the Terraform file imageupdater.tf. At the top of the file, you can find a command that can be executed in the terminal to achieve the same result. We can define the Helm release name as updater for this deployment. Then we can specify the official ArgoCD Helm repository. We can also specify the ArgoCD Helm chart that we want to deploy by setting the chart parameter to the ArgoCD image updater. When using Terraform, you don't need to use a repository alias to deploy a Helm chart. Instead, you can specify the chart name directly. In this case, we deploy updater to the ArgoCD namespace, so the next parameter can be optionally set to false. We can specify the version of the updater chart to use and then provide the path to the image update.yaml file that contains the overrides for the default chart values. Once we have defined the Helm release resource, we can switch to the terminal and navigate to the directory where the Terraform files are located. If this is the first time using Terraform, you need to initialize it first by running terraform init command. It will download all the necessary providers and initialize the local Terraform state for your project. After initializing Terraform, you can run terraform apply to install the Helm charts for ArgoCD and image updater. If you encounter any issues during the deployment process, you can try to install the Helm charts manually to identify the source of the problem. The entire deployment process should take less than a minute to complete. After the deployment is complete, you can check if all the pods in the ArgoCD namespace are up and running to ensure that the deployment was successful. Once the deployment is complete, you should see a list of ArgoCD services and a single pod for the image updater in the ArgoCD namespace. As we don't have ingress set up yet, we can use port forward to access the ArgoCD UI. While it's not necessary to use ArgoCD UI, it can be useful to monitor upgrades and identify any potential issues when getting started. When you deploy ArgoCD using a Helm chart, it will generate an admin password in the Kubernetes secret. You only need to use it once during the initial setup of ArgoCD, after which you can modify it through the UI and remove the secret entirely. The password is encoded using base64. The easiest method to decode it is by piping it to base64 utility. Do not include the % when copying, as it is only used to signify the end of the string. To log in, use admin as the username and decoded password. You can also inspect the image updater log for any errors. By now, you should have a locally running Kubernetes cluster along with ArgoCD and image updater installed. First, we'll begin with Kustomize and then proceed to deploy Helm charts in the following section. For deploying in-house applications, I typically rely on Kustomize, while for deploying certain open source projects, I prefer to use Helm charts. To begin with, let's create a GitOps repository that we can use to manage our Kubernetes cluster. Ensure that the repository is private and include a README file so that we can clone it in a later stage. Let's switch to the devel directory and clone this repository. Typically, you'll be working with private repositories most of the time. There are several authentication methods available. On GitHub, you can create a temporary token, a GitHub app, or in my opinion, the most suitable approach for CI/CD is to generate a deploy key. Firstly, we need to generate SSH keys on our local machine. If you're using older system, you may need to use RSA key. Otherwise, you can use elliptic curves. To use RSA keys, simply replace the elliptic curve parameter with RSA. You should now have both a private and a public key. The next step is to upload a public key to GitHub. Navigate to the settings and select Add Deploy Key. name it ArgoCD, and then paste in the public key. If you decide to only use internal ArgoCD method to update Docker images, you can keep this key as read-only. However, later on, when we use Git to save new updated images, we will need to have write access. Thus, make sure to grant write access as well for the time being. The next step is to open our GitOps repository. Now we can begin deploying applications to the Kubernetes cluster. Let's start by creating my app base folder. This folder will contain generic deployment objects that we can override in various environments. For instance, modifying the replica count or a namespace. This approach is solely specific to Kustomize. You can create a namespace with any name you prefer, as we will replace the namespace for every environment. Next, create a deployment object without specifying the namespace or a replica count, as we will be replacing these values later. And for the image, we'll use Nginx lesson 159. The final required object is Kustomize. In this section, we must specify which files can be overridden in each environment. In this case, we have specified the deployment and namespace files. Now that we have completed the base folder, let's create a folder structure that can be used for deploying to various environments. For instance, we can create a staging folder for deploying to the staging environment and my app folder to override any necessary parameters. For each environment, you need to create a single customized object with the properties of the Kubernetes objects you wish to modify. Using Kustomize is much more concise than copying and pasting multiple YAML files for namespaces, deployments, and services. Kustomize can also be used to modify Helm values, and I will provide an example later on. In the staging environment, we want to set the namespace to staging. For staging, we only need to create 2 pods, but for production, we may want to create 10 pods. To achieve this, you need to target deployment by its name. In this case, the deployment name is Nginx deployment, and we need to set the replica count to 2. Additionally, we need to provide initial image tag for Nginx deployment. Let's start with version 0.1.0. Finally, you need to provide the path to the My App base folder that contains all the Kubernetes objects we wish to use and modify. That's all for now. Let's commit all the files and push them to the remote GitHub repository. Remember to provide a meaningful commit messages, even if it's just a GitOps repository. Alright, we have created the base folder and customized file with overrides for the staging environment. Next, we need to set up a Docker Hub repository. You can sign up for a free account or sign in if you already have one. You only need to create image repository if you plan to upload private Docker image. For public images, you can push them right away. For this tutorial, we'll use open source Nginx image to simulate a CI/CD pipeline. We're going to use the latest tag, which is 123.4. First, we need to pull Docker image, tag it as Nginx lesson 159 and specify the tag version as 0.1.0. Additionally, make sure you use your own Docker Hub username instead of mine. Now, before you can push it to Docker Hub, you need to run Docker login and authenticate with Docker Hub. Once authenticated, you can push your new image to the remote repository. Currently, I only have a single image tag, which is important for the image updater. Now switch back to the project where we used Terraform to deploy ArgoCD and create a new folder called example1. With the image updater, you can also use app of apps pattern. Since we're using a private repo, we need to create a Kubernetes secret with the private key that we generated earlier. Make sure to update the URL to match your private GitHub repository. Then copy the private key and paste it under SSH private key. The next step is to create ArgoCD application resource for our project and name it My App. To configure updater to watch My App application resource, you need to add the image list annotation with the name of the image you want to monitor. For this example, we'll use semantic versioning constraints. We'll specify that the image updater should upgrade the application only if the patch version increases, and keep the minor version below 2. Optionally, you can add a finalizer to delete Kubernetes resources along with the deletion of the ArgoCD application object. Without this finalizer, ArgoCD will keep the pods running if you delete the application object. Specify the GitOps repository URL and path to the Kustomize file for my app. It's recommended to use branches when using image updater. So in this case, we'll be tracking the main branch. In the future, when we switch using git update method, tracking the main branch will become important for image updating. Let's specify the destination Kubernetes cluster. In this case, we'll use the same Kubernetes cluster where ArgoCD is running. This destination property is useful when deploying apps to multiple Kubernetes clusters, or when specifying a namespace for chart deployments. Finally, let's enable automatic synchronization. By default, changes need to be applied manually through the UI or CLI. Now, let's first apply the repository secret and then the application. If you create them at the same time, you may need to wait for ArgoCD to refresh its state or explicitly trigger a refresh. Alright, it seems that ArgoCD successfully pulled the private Git repository and deployed my app application to Kubernetes. Here we can see that the two pods are running in the staging namespace, and they're using 0.1.0 image tag from the Kustomize object. Let's verify from the terminal whether the pods are currently running. If you use default ArgoCD update method to update Docker images, any modifications will be saved only in the application resource. Let me show you. You can see in the specification that it uses the GitHub URL provided and the deployment path for my app. Currently, there is no Kustomize section with the image included. However, it will appear after the updater upgrades app to the next version. You can now tail the updater logs to monitor progress and identify any potential issues. By default, it will poll Docker Hub repository every 2 minutes. Certain private repositories, such as those in GCP, may be throttled, so you may need to adjust the polling frequency depending on the cloud platform where you deploy the updater. Now, let's simulate CI/CD once more and generate a Docker image with the tag 1.1. After pushing this image, it may take up to 2 minutes for ArgoCD updater to detect the new image tag. Once it detects the new image tag, the updater will update the application resource specification to include it. Then ArgoCD immediately rolls out a new version to Kubernetes. Let's examine the application resource. You can now observe a Kustomize field that contains the new image tag. Now, let's attempt to update the application's minor version. Push the Docker image and wait until the ArgoCD image updater attempts to refresh the image. As you can see, it ignored the previous Docker image. You can verify from the UI that the version is still 1.1. In my opinion, this approach of updating only ArgoCD application without committing it to Git can be potentially dangerous. In the event of disaster recovery, where you need to redeploy all apps in a different cluster, you lose all current image versions. When you reapply applications in a new cluster, they take the initial versions. Let's go through the example. Suppose you've been working on your app throughout the year and now it's at version 1.567. Let's upload this image and allow ArgoCD to update the application. Now that we have the latest version, let's imagine a scenario where something occurs causing us to lose the current application state and we need to redeploy. Let's reapply the application configuration to redeploy the app on a new cluster. The initial 1.0 version will be deployed. Within a few minutes, the image will be updated, but consider the potential damage if you had not just one but 100 of those apps deployed with a year-old outdated version. That's one of the reasons why I prefer the git update method. Remember to clean up and remove this application before we proceed to the next one. In this upcoming section, we will demonstrate how to use git update method. It will create a git commit in your application's git repository that holds the information about the image to update. I prefer this approach because it provides immediate visibility into the version of the application running in Git. Additionally, in my opinion, the previous method does not qualify as a GitOps approach. Now we can proceed to create the folder for our second example. We also need to create equivalent application resource for ArgoCD. For consistency, I will use the same name, my app. In contrast to the previous example, I will modify the semantic version constraints to update the application only when the patch version is incremented for the third minor version. Switching to the git update method is easy. You just need to include the writeback method annotation with the value set to git. The remaining components, including finalizer, source, destination, and sync policy, remain identical. As we will be using the same GitOps repository, please ensure that you create a Kubernetes secret with the SSH key in case it has been removed previously. Return to the terminal and apply the secret first, followed by the application resource itself. Just like in prior example, ArgoCD will quickly pull your GitOps repository and apply the deployment object together with staging namespace. The deployment will begin with the same initial version 1.0 as before. To ensure that semantic version constraints are respected, let's tail the updater logs and wait for the upcoming image update cycle. This will also take roughly 2 minutes. The updater has disregarded all the previous Docker tags that were created in the first example. Additionally, let's confirm through the ArgoCD user interface that we still have original 1.0 version. It's now time to test the git update approach. Let's generate a new tag 3.1 and push it to the remote Docker Hub repository. Return to the updater log and allow a few minutes for ArgoCD updater to identify the newly added 3.1 Docker tag. As indicated by the logs, updater has created a new git commit with the updated image tag. However, unlike the previous approach, updater will not directly notify the ArgoCD server. Instead, it will only create a commit, and ArgoCD will proceed with its standard cycle of monitoring the GitOps repository. In the ArgoCD UI, you can observe that the previous version continues to run. Next, let's take a look at what updater has committed to GitHub. The updater has generated a new file that will consistently use the same format. The format consists of ArgoCD source and the name of the application. Additionally, this file will be located in the environment-specific folder rather than in the base folder. Essentially, it corresponds to the source specified in the application resource. The content of this file will differ depending on whether Kustomize or Helm is being used. You can observe the same modification here as we saw in the application spec in the previous example. However, in this scenario, the change has been committed to Git along with the latest Docker image tag instead of being directly applied. You can either wait a minute or so, given that we don't have a webhook for ArgoCD, or simply click on refresh button. After refreshing, ArgoCD has deployed a new version to Kubernetes. In contrast to the previous approach, utilizing this method ensures that the latest state is not lost in the event of disaster recovery. Let's delete this application to test. Okay, it has been deleted. Now let's reapply it. In this case, you can observe that it has taken the most recent running version of the application rather than version 1.0. This aspect, coupled with the ability to see the version in Git, is why I personally prefer this update method. And of course, let's delete this application before moving to the following example. In this section, we'll use a private Docker image rather than a public one. This requires providing Minikube and Updater with access to Docker Hub repository. First, create a private Docker repository named Nginx >159 private. With a free Docker Hub account, you are limited to creating just one private repository. Similar to previous examples, we must tag the image and push it to the remote repository. The process remains the same for both public and private images. Currently, we have a single tag, which is 1.0. In this example, we will maintain the base folder and utilize Kustomize to override the image name and image tag. Create a new directory called myappprivate within the staging folder. We'll use the same staging namespace for this deployment. However, in contrast to the previous example, let's deploy only a single pod as it simplifies debugging. Next, indicate which image in the deployment you would like to modify. This should reference the original image name located in the base folder. Modify the image name to use new private image. Also, configure a default version like 1.0. Similar to the previous example, we must use a reference to the base folder. That's essentially all that is needed. As with any changes, you must add all new files to Git tree, commit and push them to remote repository. One thing to note is that you might need to pull the main branch because ArgoCD committed a file containing the image tag in the previous example. Navigate to the main workspace containing Terraform and create a new folder named example3. In this location, we must create application resource. In this case, we will use the default ArgoCD update method instead of Git, but this choice does not impact how we work with the private images. The only variation is that you must update the annotation to include the private image. Also, modify the path under the source to point to myappprivate. The remainder of the configuration stays the same. Proceed to apply this application. ArgoCD managed to successfully create a deployment. However, if you inspect it more closely, you'll discover an issue. It appears that the pod is not running and the error message is present. Get the pods in the staging namespace. Typically, image pullback off indicates that Kubernetes is not able to access the image. It may be due to misspelling or using the wrong name, or it may not have permissions to access the private image. Describing the image will show you that it's been denied permissions. To provide access, you could use your personal username and password. However, it's preferable to generate a read-only token and utilize it instead. Navigate to the security section in the account settings. And click on New Access Token. Provide a name for the token, such as Minikube, and modify the permissions to read-only. We now have a token available for use. In a later section of the video, I'll show you how to securely manage secrets in Kubernetes. However, for the time being, let's use kubectl create secret command. The type must be Docker registry. The next step involves creating the secret in the namespace where you intend to deploy the application. In this case, it's a staging namespace. Then modify the username and email and replace the password with a token that was just created. Verify that the secret was successfully created. Similar to other secrets, this one is also encoded in base64 format. To examine its content, you can use base64 utility to decode it. Next, we must update the deployment to include this pull secret. This update can be done in the base folder or through Kustomize. Add a patch section and specify the target. In this instance, the target is a deployment object. Specify the type of operation as adding a pull secret. Provide the path and value that need to be added. After incorporating all the changes, add, commit, and push them to GitHub. Navigate to ArgoCD UI, click refresh, and after a few seconds a pod should be running. Note that the status indicates that the pod is healthy. Additionally, get the pods from the terminal to verify that it's up and running. We now need to verify that the updater has the ability to access Docker Hub repository to pull any new images. Let's wait for the next update cycle. It appears that the updater does not have access. So what can be done? Updater provides support for multiple container registries out of the box. We just need to configure them accordingly. Since we utilize Helm to deploy Updater, we can add Docker Hub as a registry by specifying its values. Before proceeding, we must first create a secret that the Updater can use to access Docker Hub. You can use pull secrets, a generic secret containing a username and password, or token to achieve this. Create a secret with string data field. Include myToken property in the secret. In this case, the username will be your own and you should copy and paste the token. Let's apply this secret. It must be present in the ArgoCD namespace. The next step is to configure registry by using this secret. Under credentials, the first item is a namespace, followed by the secret name and lastly the property of the secret. In addition, this technique can be used to configure rate limits if you ever throttled by one of the public providers. We'll set it as a default, however, you can use annotations on each application to specify the registry. Now we must apply Terraform, which will redeploy the image updater. Once Terraform has finished, get the logs once again and wait for the next cycle. According to the logs, this time Updater has no issues accessing the private Docker Hub registry. Now let's test that we can update our deployment to the new Docker image. Create a new image tag such as 1.1, then push it to Docker Hub. Wait a few minutes and the updater will detect the new tag and update the deployment. In the UI, you can also observe that the new image was deployed. As I previously mentioned, later on I will demonstrate how to use sealed secrets to securely store private keys and passwords, ensuring that they are encrypted and safely stored in Git. Next, we'll examine the process of using image updater alongside Helm charts. We'll discuss deploying charts from both Git sources and Helm repositories. Let's proceed with creating a new Helm chart within the GitOps repository, which we'll use for the demo. Feel free to open it in Visual Studio or any other text editor of your choice. The default structure as follows. There is a charts folder containing child charts, also known as dependencies. Templates folder containing all templates for deployment, service, ingress, etc. Charts.yaml file contains metadata about the chart itself. Lastly, there are default values including Docker image name and tag, which we can override in this example. If you choose to use app of apps pattern with Helm, you'll usually create a chart like this one, which is similar to the base Kustomize folder, and ArgoCD application resources under environment-specific folders. In the previous video, I provided a more in-depth explanation. Now let's add the newly generated chart in the GitOps repository, commit the changes and push them to GitHub. Return to the main workspace and create a new folder called example4. The process is quite similar. To set up updater to monitor specific images, you'll also need to add annotation. As we did in previous examples, let's simply update the minor version to 4. When deploying Helm charts from a source, you also need to specify the devops repository and the path to be used, much like the process we've seen before. After that, we can utilize Helm-specific parameters to update the default Helm values. For instance, let's say I want to increase the replica count to 2. As for the image, I'll be using the same public image as in the previous examples. Of course, you can also use a private image, but it won't make any difference here. Next, let's provide initial deployment tag, such as 1.0. Under destination, you'll also need to specify the target namespace in Kubernetes, where you want to deploy this Helm chart. In my case, I'll be using the dev namespace. Regarding sync policy, be sure to enable create namespace option. That's all what we need to do. Let's proceed and apply the application. The deployment was successful, and now we have 2 pods running. We can also verify this from the terminal. Let's take a look at the updater logs. Additionally, let's create a new Docker image tag to trigger updater. It appears that the updater detected the new image tag and the deployment has been updated to use the latest 4.1 tag. We can also inspect the current state of the application object. Now, under spec section, we can see that the image tag parameter has been updated with a new 4.1 tag instead of the previous one. Things can get a bit more complicated when using Helm repositories with updater. For the next demo, let's delete this application first. In this section, we'll explore a similar example, but instead of using Git source for the chart, we'll use a Helm repository. Let's begin by deploying Chart Museum, which enables us to store charts. You can use various supported systems as a backend, such as S3. However, for this video, I won't be using any persistence. Now let's proceed to add this repository. Refresh the index. And let's search for the chart. As usual, get the default chart values and save them in a file for reference. We will modify a few parameters. First and foremost, we must enable API to allow chart uploads. The second parameter disables persistence. To deploy it, we will follow the same steps and create a Terraform file. Next, navigate to Terraform directory and apply the changes. Confirm that the Chart Museum pod is running. Additionally, use port forward command. However, since ArgoCD is running on port 8080, let's use port 8081 instead. In order to upload the chart to Chart Museum, we first need to package it. This will create an archive containing your chart source. We can use curl with binary data to upload the packaged chart. This step is not required, but it can be used to confirm that the chart was uploaded successfully. It appears that we now have the chart. Let's create a new folder called example5 and application resource. We'll use the same annotation and the same Docker image. Instead of specifying the branch, we can now use the chart version and replace the Git source with Chart Museum. Then we'll use the same parameters to override the image name and tag. For this demo, let's use prod namespace. That's it, let's go ahead and apply the changes. The Helm chart was deployed successfully with the initial version of 1.0. To test Updater, let's release a new version of the application. Wait for the next update cycle. Then verify from the UI that the image has been updated. You can also find the updated tag under the spec section. Now, you can only use git update method when deploying Helm charts from git source and not from Helm repository. There is a workaround that involves using app of apps pattern and Kustomize, but it's best to wait until it's officially supported by ArgoCD. In this section, I'll describe the process of securing your sensitive data through encryption and storing it in Git. To do this, we'll use a tool called Sealed Secrets Controller, which generates a key pair. We'll use the public key to encrypt our secrets, and when we apply the encrypted secret, controller will use its private key to decrypt it and convert it back to a regular secret. For deployment, we'll use Bitnami Helm chart. I'll keep all default values. If you want to override any of them, you know the steps. Let's go ahead and create a Terraform file to install Sealed Secrets Helm chart. We'll place it in kube system namespace. That's going to be important for the kubectl CLI. That's it. Just run Terraform apply now. The controller will be deployed in just a few seconds. Quickly verify if the pod is running. kubectl CLI will use this service to get a public key for encrypting secrets. If you have a different name, you'll need to adjust later on. If you're using Mac, you can install it using Homebrew. Installation instructions for most operating systems can be found in the README file. To test, let's consider the first example where we created a Kubernetes secret with a private key from a GitHub repository, and ArgoCD used it to clone that GitOps repository. Now let's delete it. Let's try to create this application. This application uses a private Git repository. Let's apply it. If you check the UI, you'll notice that there is an issue. ArgoCD is unable to clone the repository. The reason for this issue is that we deleted the secret. To resolve this issue, we'll convert this Kubernetes secret to a sealed secret that can be safely stored even in the public Git repository. I'll create another folder for this sealed secret. To seal the secret, use the following command. Specify the namespace and, most importantly, provide the name of the controller, which is the Kubernetes service for the sealed secret controller. Next, encrypt the secret. Let's take a look. Now we have a sealed secret that is encrypted with a public key. Remember, you cannot simply copy and paste this secret and apply it to all your Kubernetes clusters. It is specific to this cluster. To apply it, we'll use a regular kubectl apply command. Then the controller detects this sealed secret and decrypts it. Now we have the lesson 159 secret back. Let's go back to the UI and refresh it. That's all. As you can see, it's very easy to store secrets securely using sealed secrets. Thank you for watching, and I'll see you in the next video.